So this is where we're going to talk about Hamilton paths and circuits. Now, to contrast Euler paths and circuits, so this is what we were doing previously in this course, Euler paths and circuits require that we include every edge of the graph once and only once. Hamilton paths and circuits are going to shift our focus. On a Hamilton path or circuit, this is going to require that we include every vertex of the graph once and only once. So remember when you were bouncing around on your Euler path or circuit, we had said that you could repeatedly come back to a vertex as long as there was a new edge that allowed you to get out of it? That's not going to happen anymore in these Hamilton ideas. Once you visit a vertex, you're never allowed to go back there. Now let's compare and contrast Euler ideas with Hamilton ideas just to help us designate what's going on that's different between these two. So first off, in this graph right here, is there an Euler circuit? So as a reminder from Euler's theorems, an Euler circuit exists if all of the vertices are of even degree. So I'll come through here and record the degree of all these vertices. This guy has degree 2, this one has degree 4, that one has degree 4, this one has degree 4, that one has degree 2, this one has degree 4, and that one has degree 4. So does an Euler circuit exist? Yes, it does. All the vertices are even degree. Now, does an Euler path exist? Yes, if an Euler circuit exists, an Euler path exists as well. Now, does a Hamilton circuit exist? So what a Hamilton circuit will be on this graph is I have to be able to start at a vertex, I have to be able to go to every other vertex of the graph once and only once, and I still have to satisfy this circuit idea of being able to get back to my starting vertex. So is this graph going to have a Hamilton circuit? So you can take a moment to try to find one, and you're going to find out that yes, it does. All right, so here is going to be an example of a Hamilton circuit. So I'm going to start here at B. I'm going to go up to F, over here to A. Maybe I'll go over to E next, then to D, down here to G, up to C, and then come back home to B. There is an example of a Hamilton circuit. So notice for this Hamilton circuit, you don't have to use every edge of the graph, because that's not what we're concerned about. What we're concerned about is that you have to go to every vertex in the graph. And I was able to do that. Now, for a Hamilton path, the only requirement for a Hamilton path is that you were able to go to every vertex in the graph once and only once. And I was able to do that too. I was just able to have an added criteria of not only was I able to go to every vertex of the graph once and only once, I was able to get back to where I started. Okay, so this graph will have a Hamilton path as well. So let's take a look at this next graph. Will this graph have an Euler circuit? Let's go ahead and find the degree of the vertices. A has degree 2, B has degree 2, E has degree 2, D has degree 3. Okay, so at this point in time this does not have an Euler circuit. But C has degree 1, so Euler circuit, no, but Euler path, yes. There are exactly 2 odd vertices. So it is possible to start at one odd vertex, travel every edge of this graph once and only once, and then I would have to end at the other odd vertex. So maybe as an example, and I'm going to erase this, but so you can see the Euler path. Maybe I start here at C, so I can go to D, A, B, E, and then end up at the other odd vertex. Okay, so notice I was able to use every edge of the graph once and only once. That would be an example of an Euler path on this graph. Now let's take a look. Does this graph have a Hamilton circuit? So is it going to be possible for me to start at a vertex, visit all the other vertices, and get back to that starting vertex? So if we were to try a couple of them, maybe I start here at B, so I have to go to A and then D. Now if I try to go out here and grab C, this is going to be a problem. I can't come back to a vertex I've already been to. So this isn't going to work as a Hamilton circuit. Maybe I'll start out here at this vertex. Well, there's going to be a problem. So remember, for a circuit, you have to be able to come back to that starting vertex. So if I start here at C, and I go to D, then A, then B, then E, I've got to come back to C. And the only way I can get back to C is I've got to go through D, and I've already been there. So that's not going to work. So you could try a couple more examples, and you're going to find out, does this graph have a Hamilton circuit? The answer to that question is going to be no. But does it have a Hamilton path? Yes, it does. And we actually just found one. There is a way for me to hit every vertex of the graph once and only once. So maybe as an example of a Hamilton path, this is not the only one that exists. So maybe I'll start here at C. I'll go to D. We'll come up to A. Over to B. And then I'll end at E. So I was able to visit every vertex of the graph once and only once. Let's take a look at this final example. Does this graph down here have an Euler circuit? This vertex right here is degree 3. So no Euler circuit because I have odd degree vertices in here. This one will also have degree 3. This one has degree 3. Yeah, I have more than 2 odd vertices in this graph. So does it have an Euler circuit? The answer to that question is no. Does it have an Euler path? The answer to that question is also no, because I would need to have exactly 2 odd vertices. Let's move on to the Hamilton ideas. Does this graph have a Hamilton circuit? We're going to find out that yes, it does. Okay, so see if you can come up with a Hamilton circuit on this. So here's an example of one. I'm going to start here at B, go to A, maybe down here to D, up to E, come over here and grab C, and then back home. So it has a Hamilton circuit, and it will also have a Hamilton path. Now, as a reminder, all Hamilton circuits are also Hamilton paths. The only thing that for a Hamilton path that's required is that you have to have a path, so you're traveling a series of adjacent vertices, and you have to be able to grab every vertex exactly one time. And I was able to do that here. So the circuit is more restrictive because you have to start and end at the same vertex. So we could also just find Hamilton paths that are not circuits. So maybe as an example of a Hamilton path that's not a circuit. How about A, B, E, D, C? So to maybe visualize it, A, B, E, D, C. So in that one, I was able to grab every vertex of the graph once and only once. And this would not be then classified as a circuit because you started and ended at different vertices. So in these examples, you're seeing that there's graphs that could have Euler and Hamilton, graph that has some of the Euler and some of the Hamilton, graphs that have no Euler and no Hamilton. So there's actually no rhyme or reason in terms of the existence of one implicating the existence of something else. The only exception would be if there's an Euler circuit, there is definitely an Euler path. But notice it's not the other way, right? You could have a graph that has an Euler path but not an Euler circuit. And then for the Hamilton ideas, if there is a Hamilton circuit, there will be a Hamilton path. But again, there could be graphs that the other way doesn't hold true. There are Hamilton paths but no Hamilton circuits. Now, Euler gave us some cool theorems to be able to tell whether or not there's Euler circuits or Euler paths by looking at the degree of the vertices. So you might be waiting for the big reveal in terms of, okay, how can we tell whether or not there's Hamilton circuits and Hamilton paths in the graph? Okay, so quite honestly, there is going to be no easy algorithm to determine if these exist in a graph. So you're just going to have to kind of dink around on the graphs and see if you can find a Hamilton circuit or a Hamilton path. There's not going to be something where we're going to look at the degree of the vertices or, the relationships or whether or not there's bridges or anything like that. Now, eventually moving forward, we're going to look at a special type of graph, which is called a complete graph, which will always have a Hamilton circuit in there. But otherwise, if you're not looking at a complete graph, you're just going to have to look at the graph and see if you can find a Hamilton circuit or path. Now, something else that's a little bit different about these Hamilton ideas. So these graphs are a repeat of that last one we were looking at. Let's list two different Hamilton circuits. Now, you might be able to come up with several, but I want to highlight two particular ones. So one of the Hamilton circuits I'm going to state is going to start at A, go to B, then to E, then to C, then to D, and then back to A. So this one, if I were to maybe put this on the graph with arrows, I said I'm going to go from A to B, B to E, E to C, C to D, and then D back to A. There's an example of a Hamilton circuit. A different Hamilton circuit would be from A to D. Okay, so from A I'm going to go to D. From D I'm going to go to C. From C I'm going to go to E. E to B. Then B back to A. So what we're seeing here in this example is that the direction that you travel matters. Moving forward, we're going to count these as two different Hamilton circuits. Now, there is a relationship between them, especially when we get into weighted graphs, so I will tend to call these two types of circuits, I'll be calling these mirror images. They're grabbing the same edges in the graph, but I'm just traveling through the graph in a different order, specifically the reverse route. So we're going to count these as two different Hamilton circuits. Now, over here, we're going to state the same Hamilton circuit two different ways. So I'm going to start with the same one that we were just looking at, A, B, E, C, D, A. So I'm going to draw it on here, A, B to E, E to C, C to D, D back to A. I'm going to state the same circuit a different way. How about this? E to C, C to D, D to A to B, and then back to E. So what we're saying on this one is that changing the starting vertex is not counted as a different circuit. So we're going to have a lot of them that we're going to record the direction. So here's where you're seeing that staggering, that starting vertex is not going to be counted differently. So again, I could have started this circuit at A, I could have started at B, E, C, or D. And all of those would be counted the same because I'm basically kind of flowing through this graph the same way. Notice if you were just looking at the vertex letters, I would go from E to C, C to D, D to A, swing back over here to B, and then B to E. So I could then just look at these letters and then come up with the same Hamilton circuit that looks different, but it's counted as the same. So for instance, I could go from D to A to B, B to E, E to C, and then C back to D. So these ideas are going to be important as we start talking about complete graphs. So let's summarize what we're seeing right now between Euler and Hamilton. So for a graph that I'm looking for perhaps an Euler circuit or path, oh, come back here. For Euler ideas, can we repeatedly visit a vertex? Yes, we can. What about if I'm looking for Hamilton ideas? Can we repeatedly visit a vertex? No, we cannot. Now, the exception is that starting vertex if you're looking for a circuit, because you have to close your circuit up. But otherwise, no, you can't ever repeatedly visit a vertex you've been to before. For Euler graphs, can we travel along an edge more than once? No, that's the foundation for this Euler concept, that you hit each edge once and only once. What about for a Hamilton graph? Can you travel along an edge more than once? Well, we're going to find that one is also no, but it's no because you can't repeatedly visit a vertex. So the only way you can travel an edge more than once is you would have to visit the same vertex more than once. So no, on these Hamilton ideas you won't be able to travel along an edge more than once either. For Euler graphs, can you omit vertices, which basically means you don't go to a particular vertex in the graph? No, you cannot. As part of grabbing all of the edges, you have to then hit all the vertices. For Hamilton graphs, can you omit vertices? No, that's the foundation of these Hamilton graphs, is that you have to go to all the vertices. So in terms of like the kind of the key concept, travel along an edge more than once, that's exactly what Euler doesn't allow you to do. Repeatedly visiting a vertex, or sorry, omitting vertices, that's exactly what Hamilton won't let you do. Okay, so these are kind of the key ones on these two different concepts. Now this last one, can you omit edges? So you basically don't grab an edge in the graph. For Euler, nope. Again, that's kind of a fundamental thing. You have to travel each edge once and only once, so you can't leave any of them out. And then for Hamilton graphs, can you omit edges? Which basically means you don't grab certain edges in the graph. Yes, on that, that's true. So here's an example of one. I didn't ever grab this edge right here. Okay, so we're seeing some similarities, but some key differences between Euler ideas and Hamilton ideas.